Statistics is the study of how you collect, analyze, and draw conclusions from your data sets. So it can be used to bring the future into focus and answer key questions about your data set. So welcome back to the channel and welcome to Excel Island, where the goal and objective is to learn and master Python over the next 100 days. And today is day 45. So we've been learning all about Python over the past 45 days, which we do daily, just basically for 1 hour or at least a few minutes over an hour every day and the plan is to do that over the next 100 days. We are on our 7th course in this Python for data analysis curriculum on DataCamp, which is Introduction to Statistics. And we are on the 2nd chapter of this course. So each course in the whole career track has at least 4 chapters. You get it now? So we are on the 2nd chapter of the 7th course. So we have 3 more courses to complete the whole career track on introduction on data analysis rather with Python on the DataCamp platform. So in this introduction to statistics, we looked at summing statistics in chapter 1, where we actually look at how to explore summing statistics, including mean, median, and standard deviation, and we learned how to accurately interpret these statistics or concepts rather. So we also looked at, so we're on the 2nd chapter, which is random number and probabilities. So we learned how to generate random samples and measures using probability. We're working on a real world data set to calculate the probability of a salesperson being successful. So that's what we're actually doing in this 2nd chapter of this introduction to statistics. So without further ado, I'm just going to continue from this 2nd chapter and start sharing my screen immediately. So this is the Python environment we are using. So all these data sets is already linked under the YouTube description. So you can have access to all these data sets for this introduction to statistics in Python, which is the 7th course in this career track. So I'm just going to continue from here immediately. So we are on the chapter 2 of the course of this course, Introduction to Statistics. So we just continue immediately from this concept. So we've actually looked at what are chances. We learned all about doing probabilities with or without replacements. We calculated probability. We did some discrete distribution, and we created the probability of distribution and did a lot of stuff also. So you can catch all of this on the previous live stream, which is day 44 and 43, where we went deeper into these random numbers and probability. If you want to have more knowledge about summing statistics, which is what is statistic, descriptive, and inferential statistics, just go a couple of live stream or backward for that. So let's look at continuous distribution in this concept. So this is where we stopped from the previous live stream. We're just going to continue from here where we stop on day 44. So welcome back.
We can use discrete distributions to model situations that involve discrete or countable variables. But how can we model continuous variables? Let's start with an example. The city bus arrives once every 12 minutes. So if you show up at a random time, you could wait anywhere from 0 minutes if you just arrive as the bus pulls in, up to 12 minutes if you arrive just as the bus leaves. Let's model this scenario with a probability distribution. There are an infinite number of minutes we could wait, since we could wait 1 minute, 1.5 minutes, 1.53 minutes, and so on. So we can't create individual blocks like we could with a discrete variable. Instead, we'll use a continuous line to represent probability. The line is flat since there's the same probability of waiting any time from 0 to 12 minutes. This is called the continuous uniform distribution. Now that we have our distribution, let's figure out what the probability is that we'll wait between 4 and 7 minutes. Just like with discrete distributions, we can take the area from 4 to 7 to calculate probability. The width of this rectangle is 7 minus 4, which is 3. The height is 1/12. Multiplying those together to get area, we get 3/12, or 25%. Let's use the uniform distribution in Python to calculate the probability of waiting 7 minutes or less. we need to import uniform from scipy.stats. We can call uniform.cdf and pass it 7, followed by the lower and upper limits, which in our case is 0 and 12. The probability of waiting less than 7 minutes is about 58%. If we want the probability of waiting more than 7 minutes, we need to take 1 minus the probability of waiting less than 7 minutes. How do we calculate probability of waiting 4 to 7 minutes using Python? We can start with the probability of waiting less than 7 minutes, then subtract the probability of waiting less than 4 minutes. This gives us 25%. To calculate the probability of waiting between 0 and 12 minutes, we multiply 12 by 1/12, which is 1, or 100%. This makes sense, since we're certain we'll wait anywhere from 0 to 12 minutes. To generate random numbers according to the uniform distribution, we can use uniform.rvs, which takes in the minimum value, maximum value, followed by the number of random values we want to generate. Here, we generate 10 random values between 0 and 5. Continuous distributions can take forms other than uniform, where some values have higher probability than others. No matter the shape of the distribution, the area beneath it must always equal 1. This will also be true of other distributions you'll learn about later on in the course, like the normal distribution or exponential distribution, which can be used to model many real-life situations. Time to practice working with continuous distributions.
Oh, so there are basically different types of distributions. So we've actually looked at a discrete distribution. So we are on what is called a continuous distribution. I think there's also something called binomial distribution. So let's see who we need to compare here. So with distribution, so at this point, you've learned about the two different variants of uniform distribution, the discrete uniform distribution and the continuous uniform distribution. So in this exercise, you decide which situations follow each distribution. Wow, that's good. So this is discrete uniform, continuous uniform. So map each situation to the probability distribution it will best be modeled by discrete or continuous. The height of a random person. The height of a random person. So we need to know that so the height of a random person, a minute. So the person is random. So since the height of a random person it is continuous, since the height can fall within any range, so we can't specifically know which part the height is going to fall into. Okay. The ticket number of a raffle winner, assuming there is one ticket for each number from 1 to 100. Hmm. So that would be a discrete because it's going to, you can't know which number uh the ticket number is going to fall into. But we know that the tickets, there is one ticket for each number from 1 to 100. Okay, the time you have to wait for a geyser to erupt if you show up at a random time, knowing that the geyser erupts exactly every 10 minutes. Okay. Hmm. Okay. Let's see. The height you have to wait for a geyser to erupt. So probably a geyser is an animal that will show up from wherever it is hiding. But we know that the geyser erupts exactly every 10 minutes. So every 10 minutes, let's go for continuous. So the outcome of a rolling sided die. The outcome of a rolling sided die. That will be a discrete distribution. But the time of the day baby will be born. Ooh, the time of the day. The time of the day baby will be born. You can see this is orders. Uh, okay, let's go for continuous. Let's see. Ooh, we missed this. The height of a random person. A random person's height. Try again. Is someone equally as likely to be 5.5 feet as they are 7 feet? Oh, so we missed this height of a random person. Would that be a discrete? Will we say it is a discrete so that it is orders? Oh, okay. What would height of a random person now fall into? Height of a random person. Probably it is a binomial distribution because you've not learned about the concept of binomial distribution. There's binomial distribution here. Probably that's why I feel that. Okay, let's give it a shot. Exactly. Awesome work. In the next exercise, you you work specifically with a continuous uniform distribution. Continuous uniform distribution. Okay, let's continue. So data backs up. So the sales software used at your company is set to automatically back itself up, but no one knows exactly what time the backups happen. It is known, however, that backups happen exactly every 30 minutes. So a mail comes back from sales meetings at random times to update the data on the client he just met with. So he wants to know how long he will have to wait for his newly entered data to get backed up. Use your new knowledge of continuous uniform distribution to model this situation and answer a mail question. So to model how long a mail will wait for a backup using a continuous uniform distribution, save its lowest possible wait time as minute time and its longest possible wait time as max time data frame. Remember that backups happen every 30 minutes. Oh, okay, interesting. So every 30 minutes. So the minimum will be 0 and the maximum will be 30 minutes if you want to use the concept like that. So let's see. So the minimum is definitely going to be 0. So the minimum wait time. Oh, I have the data set here, but let's see. I have the data set somewhere here. So we have this sales data set somewhere here. We could model the same thing here. We're just doing random sampling here the other time. So we did all of this on the first day of this introduction to statistics when we started the summing statistics concept. So let's say minimum and maximum wait times for backup that happen every 30 minutes. Let me just run this line of code again. So we've learned all about pandas. We've learned how to use pandas. We've learned how to use NumPy. We've learned how to use matplotlib. So we just learned one recently, which is SciPy. From SciPy, just start import uniforms. Let me just add it to the name of the library I've learned from. So from SciPy dot stats. So that means you can import different different maybe data frames or functions from this sci-fi that starts. So we want to import uniform. Let's see. It works fine. So we've learned how to use all these libraries. So these are the libraries you use to work with your any data set you import in Python. These are the previous code I've run. So let's continue from here. So we know that the lowest possible wait time is 0 minutes, is 0, and the maximum wait time is 30 minutes. So let's run the code. I'm just going to copy this for here. So I'm going to try it in my Jupyter notebook here. Okay, let's see. So model alarm will wait for back within a continuous uniform distribution. Okay, so I want to copy this line of code here, this block of. So I just like to, so I like to model something. So I want to try it say in my own Jupyter notebook too and see it in action. So we got that. So the next instruction say import uniform from scipy or sci-fi.stats and calculate the probability that a meal has to wait less than 5 minutes and store in a variable called probability of waiting, probability less than 5 minutes. Okay. Import, okay, I've import this library. So you say we should import a uniform from sci-fi. So from sci-fi dot stats import uniform. So now calculate the probability of waiting less than 5 minutes. Probability of waiting less than 5 minutes would be let's see how, so we want to use uniform. Let's see how to calculate that in Python. So it's going to be uniform. So the code is going to be uniform. Uniform open bracket dot cdf open bracket. So the maximum wait time. I think the minimum wait time is uh minimum. It has to be the minimum first. Let me see. Let me see how to do that. So I'm just checking my files here. So that would be the minimum time. So minimum time has to come for which is 5, which is probably less than 5. Okay, we want to calculate the probability of a meal. A meal has to wait less than 5 minutes and store in a variable called minimum. So 5 minutes. Then the minimum time is 0. So you can just call on this minute time here. Mean time. Mean time. And the maximum time is 30 minutes. That should be max time. Let's see if we get that. So the probability of him waiting is 16, probably less than 16% or 1.6%. Let's see if we guess, if we got the calculation. Good, we nailed the calculation there. So what we did there was we did a probability, we want to calculate the probability that our meal has to wait less than 5 minutes. So that's why we imported this 5 number here. Then for this uniform function, we need to provide the minimum time, which is 0 minutes, and the maximum time, which is 30 minutes. So we calculated the probability is as simple as that. So that is 16%. So let me give it a shot here. Let's give it a shot here. So if I print probability of less than 5 minutes, so it give us what you can see, 16%. So let's move on to the next instruction. So calculate the probability that Ami has to wait more than 5 minutes and store this in a variable called probability greater than 5 minutes. So I want to calculate probability greater than 5 minutes. That's be uniform dot CDF open brackets. So we have to do one minus probability less than 5 minutes to get the probability of waiting more than 5 minutes. So I'm going to do 5 minutes, then the minimum time and the maximum time. Let's see. So probability of it waiting more than 5 minutes is 83%. Interesting. So we know that the minimum probability of waiting less than 5 minutes is 60%. So we're going to minus 1 minus probability of him waiting more than less than 5 minutes to calculate probability of him waiting more than 5 minutes. Okay. So that probability of him waiting more than 5 minutes is 83%. Since the minimum time is 0 and the maximum time is 30 minutes. That's probably be waiting close to 25 minutes for that backup to happen. Okay. Now let's calculate probability of that our meal has to wait between 10 and 20 minutes and store it in a variable called between 10 and 20 minutes rather. Oh, okay. I was going back there. So I'm going to use uniform. So uniform dot CDF open bracket. So the highest minutes that I want to calculate probability is 20 minutes. Like we need to wait more than between 10 and 20 minutes. So we want to calculate probability of him waiting between 10 and 20 minutes. So uniform the CDF 20 minutes minimum time, comma the maximum time. So that will be minus uniform dot CDF dot CDF. The probability of him waiting between that is 10 and 20 minutes. The minimum time, and the maximum time. So let's give it a shot. So the probability of him waiting between 10 and 20 minutes is 33%. Interesting. Let's submit that. Oh, great. So we nailed that simple probability calculation there. So probability of Amir waiting between 10 and 20 minutes is 33%, based on the fact that the minimum time is 0 minutes and the maximum time is 30 minutes. So we just use this from sci-fi.start import uniform to calculate all this probability uh, concepts here. So wonderful wait time calculation. So there is 33% chance that a male will wait 10 and 20 minutes. So in the next exercise, you will make sure this calculation hold up by simulating some wait times. Okay, let's see. Oh, we've been learning over the past couple of days. So simulating wait times. So we want to set a random seed and do some stuff here. So let's see. So we've been on the live stream for over 20 minutes now. Okay. But let's do this. If possible, we can do this by linear distribution and end this concept of probability today. Okay, let's see. So to give a meal a better idea of how long you have to wait, you will simulate a meal waiting 1,000 times and create a histogram to show him what he should expect. Recall from the last exercise that his minimum wait time is 0 minutes and his maximum wait time is 30 minutes. As usual, pandas as PD, numpy as MP, and matplotlib as pyplot. Matplotlib.pyplot as PLC are loaded for you. So these are all the libraries we'll be using, we'll be learning from the beginning of this Python knowledge. So these are the libraries you use to work and manipulate your data sets, create visualization. So this is for data manipulation. This is for what's numpy used for? Funny, and I can't remember. But this is for data manipulation. Pandas NumPy is used for something. I can't remember right now. So matplotlib is used for data visualization, and this sci-fi.start is used for statistics. So I will definitely remember what NumPy is used for. So it skipped my mind. Let's see what we need to do here to complete this last session. So we need to set a random seed of 334. So we need to set a random seed. So that'll be np.random. So that's what NumPy is used for. np.random. So np.random seed. So let's set the seed of 334. Okay. So to give me a better idea of how long you have to wait, you simulate a meal. You want to simulate a meal waiting 100 times and create an Instagram to show him what to expect. Okay, let me just copy this and paste it here in my Jupyter notebook so I can understand what I am doing there. Okay. Let's run the code. So we set a random seed for that. Let's do the same thing here. So this is what we use NumPy for. So we are using NumPy at the beginning of this analysis here. Let's see that. So import uniforms from sci-fi.start. So import from sci-fi.start. Import uniform. So we've done that before. So we need to generate 1,000 wait times from the continuous uniform distribution that models our meals wait time. Save this as wait times. So we need to save this as wait time. Generate 1,000 wait times between 0 and 30 minutes. So between 0 and 30 minutes, we want to create a mail coming into the office for the backup 1,000 times. That's interesting. So wait times is going to be np.random.uniform. So between 0 and 30 minutes, so 0 and 30 minutes, so generate 1,000 wait times. Oh, okay. Let's see. Let's run the code of what I can see. So it just generated random wait times for us there. Wait times. So if I call on wait times now, underscore times, you see. So it generated random numbers 1,000 times. So these are different wait times. This is probably 8 minutes, 27 minutes, and so on and so forth like that. So that is the size. So between 0 and 30 minutes, we want to generate 1,000 random wait times. So within that, I could just do something like this. Wait times dot edge. Hopefully it's going to work also. Oh, it didn't work. So I can't do that. So I have to call on my wait times normally. Okay. So let's continue from there. So create a histogram of the simulated wait times and show the plots. Okay. Well, I could even add size. I didn't add size here in my own line of code. So okay. So but it knows the size. It gets what I was trying to do there then. So let's put the size concept here. I say size equals to 1,000. So you're having the same. So it's going to be random numbers generally for different times. Okay, that's interesting there. So our histogram of the wait time is going to be plots plt.is. I'm going to say wait times, the number of beans. I can just specify the number of beans to be equal to 30. Since it's within 30 minutes, okay, let's do plt.show. So I don't want to label the charts. So I can say plt.show. Let's see what we have here. You can see, so as you can see the different wait times. So we've simulated 1,000 wait times within 30 minutes, 0 to 30 minutes. Interesting. Let's submit and see. So Subab simulating, unless Amil figures out exactly what time each backups happen, he won't be able to time his data entry. So it gets backed up sooner. But it looks like it will wait about 15 minutes on average. Yes, on average, it has to wait about 15 minutes. Okay, now let's simulate same scenario in my Jupyter notebook here. You can see we have same thing. You can see exactly same thing. But on average, it should be 15 minutes also. But on average, it could be probably 16 minutes because that is the highest here.